All right, here we're going to talk about designing experiments, and we're going to start with a little review of significant digits. So, how many significant digits are in the number 0.0504 kilograms? 3. This is the dot right rule. So I read the number to the right, and I don't count lead zeros. So I don't count that one, and I don't count that one. So 3 significant digits. What is 12.4 minus 3.61? 8.8 is the correct response because we only have one decimal place here. And so when we add or subtract, we have to make sure that our result has the same number of decimal places as the measured value that is least precise. What is 110 meters divided by 3.0 seconds? 37 meters per second. When we multiply or divide, we have to make sure that the result has the same number of significant digits as the initial value with the fewest significant digits. This is the value, or rather this value has 2 significant digits. This value has 2 significant digits as well. So our result has to have 2 significant digits. And we have to round appropriately. So designing experiments and dealing with data. When we do an experiment, really what we're trying to do is answer a question or solve some kind of a problem. Often in physics, we're trying to find the relationship between 2 physical quantities, and the question that we use has to be specific. Here's a bad example. What affects the period of a pendulum? If we tried to use that question to design an experiment, it would be really complicated because there may be thousands of different factors that might affect the period of a pendulum. Here's a better one. What effect does the mass of a pendulum have on the period of the pendulum? So that's much more specific, and we can design an experiment to try and answer that question. We'll be changing the mass of the pendulum bob, and we'll be measuring the period of the pendulum. That means that the mass is the independent variable in this experiment, and the period is the dependent variable. We also have what we call constant variables in an experiment, which must be controlled. These are things that we have to make sure do not change during the experiment. So they're constants. Here's an example. The length of the pendulum, we would keep that constant in our experiment if we're only looking for the relationship between mass and period. Another example would be the displacement of the pendulum and the number of swings that we count. Displacement meaning how far do we pull it over before we let it go. A hypothesis is really a prediction of how the changing independent, or how rather changing the independent variable will change the dependent. So, and that of course depends on the experiment. And you should use some previous knowledge about the topic in order to make your hypothesis. In other words, it shouldn't just be a guess. So what effect does the mass of a pendulum have on the period of the pendulum? Well, you might think, I know something about gravity, and if something has a greater mass, then the force of gravity will be greater. Something is heavier if it is more massive, after all. So a reasonable hypothesis might be if the mass is increased, then the period of the pendulum will also increase, because it's harder to move, so it perhaps will swing more slowly. In the procedure, we always specify the values of the constants. For example, the string attached to the pendulum was 1 meter in length, 1.0 meters in length rather, and the pendulum was displaced by an angle of 10 degrees from the equilibrium position. The time for 10 complete swings was measured using a stopwatch. Here we have, you'll notice as well that we use past tense for the procedure. So past tense is used, attached to the pendulum, and we don't make any mention of who's doing the experiment. And we also indicate how we're making our measurements, so measured using a stopwatch. That's important too. Because after all, the point of having a detailed procedure is so that other people can repeat our experiment exactly the same way that we did it. In the procedure, we should have at least 5 values for the independent variable, and we need at least a factor of 2 difference between the largest and the smallest. So here's an example. We select masses of 50 grams, 100 grams, 150 grams, etc., up to 250 grams. These are good choices. So these choices right here are good because the biggest value is 5 times bigger. There's a factor of 5 between the smallest value and the biggest value. That's more than meets our requirement of a factor of 2. If we choose 50 grams, 55 grams, and 60 grams, that doesn't meet the requirement. And that's because if the changes aren't big enough, we may not notice a difference with our experiment if we're looking at what happens to the dependent variable. In any experiment, when we make measurements, we have what's called experimental error. And you want the differences between your values to be larger than the experimental error. So if we have a situation like this, it's difficult to determine what the relationship is because, for one thing, we only have 3 pieces of data. That doesn't give us a lot of information. When we talk about experimental errors, we are not talking about mistakes that people make. So we don't talk about human error. When we're asked for sources of error, we never put something like, we might have measured the time wrong, or we might have measured the distance wrong. Measuring something wrong is not experimental error. That's a mistake. And if you make a mistake when doing an experiment, then you just go back and you repeat that part and you don't make the mistake the second time. Experimental errors, instead, really are uncertainties. That's another name for them. They're limitations on the accuracy and precision of any measurement that we make. And every measured value has an uncertainty. For example, reaction time when measuring something with a stopwatch, there's an uncertainty with that, largely based on how quickly someone can react when starting or stopping a stopwatch. Or some physical things that go on in the experiment, like wobbles in the swing of a pendulum. If you're using a retort stand, it could be that the retort stand was wobbling a bit, so maybe the pendulum wasn't just swinging back and forth, maybe it had some circular motion as well. Fortunately, we expect that the measurements will be distributed more or less randomly about the actual values, kind of like taking shots at a target. That's why we do multiple trials of an experiment or a measurement and then average the results. If we could do hundreds and hundreds of trials, then the more trials we do, the better our results should be, because our average should be that much closer to the actual value that we're looking for. Here are some strategies to help us reduce the effects of error when setting up an experiment. So if we let the pendulum in this example swing more than once and then divide the time by the number of swings, that would reduce the effect that reaction time errors have, because the total time is bigger. So if you were to time only one swing, then your reaction time compared to the time of one swing is quite large. But if I time 20 swings, well, my reaction time is still the same. And so that error is very small compared to the time for 20 swings, because the time that I measured is 20 times bigger than it would have been if I just timed one swing. When we do experiments, we have a couple of different kinds of observations, and you've probably heard about these before. qualitative observations are just descriptive. So we could say the amplitude of the pendulum decreased slowly over 10 swings. There are no measured values associated with that measurement. If we do measure values, then those are quantitative observations. So something like the mass of the pendulum was 150 grams. That's a quantitative observation. We can record both of these kinds of observations in tables, and tables are really a great way to organize our data, so we'll use them a lot in physics. Here we have position time information for a dynamics cart that's moving on a level surface. And so we title the table properly. Table 1, we always number the table. We always put units in, so there's our number of the table. We have a descriptive title, so check, descriptive title. We also include units in the table. Our tables, as I said, need to be numbered. They need to be titled descriptively, so the title has to have some meaning and tell us what the table's about. They need to be drawn with a ruler, and so the rows and columns have to be outlined and nice and neat. And the rows and columns have to be identifying, so they have to include units and tell us what quantity is stored in each of those columns or rows. Often when we're looking for a relationship between two quantities in physics, we'll take that data, those numerical data, and we'll plot them in graphs or a graph. And so here's an example. If we plot distance versus time for those data that we just looked at, then we might get a graph that looks something like this. Graphs also need to be numbered, so graph number 1, they also have to be titled descriptively, so we could say distance versus time graph for the moving dynamics cart. And they have to be large enough to take up at least half a page. A full page is better. If you have a full page piece, just use a full piece of graph paper. That's a good way to do it. That means that the points should take up half the page, not huddled in one corner. So you want to choose your scales on your graph so that the data points fill up the entire half page minimum, because the more room those data points take up, the more accurate your results will be. You have to make sure that you label the axes properly with the variables and the units. And unless you're otherwise directed, the independent variable should be placed on the x-axis, or the horizontal axis, and the dependent variable should be on the vertical axis, or the y-axis. There are some occasions in which we'll reverse those, but you'll be told when that happens. And that's really because there's a convenience. When we're looking for certain relationships, sometimes it's easier for us to switch them. Some other things to think about with graphs: the scale should be in multiples of 1, 2, or 5, because that makes them easier to read. And again, choose that scale to fill as much of the page as possible. The points should be plotted in pencil with a circle around each sharp dot, and that circle represents the uncertainty we talked about. So if I see a graph that you've made that has circles around it, I know that you're doing science and not math, because every measurement we make in science has an uncertainty. A ruler drawn line of best fit should be then drawn, or a curve of best fit if you think that it's a curved shape. If you're uncertain, then ask the teacher. We can give you some good guidance there. If 0, 0 is a known data point, then you can use that information. Otherwise, you should omit 0, 0. Once we have our graph made, we'll look at the shape of the graph, and it will tell us a lot about the relationship we're looking for. So these are the 4 most common shapes of graphs. Here we have a linear graph, and you've seen those before. This tells us that as the independent variable increases, the dependent variable increases linearly. So if I double the independent variable, then that tells me that the dependent variable also doubles. If we see a graph with a curve like this, it tells us that as the independent variable increases, the dependent variable increases at an increasing rate. So we can see the slope of the graph is increasing, and that's our indicator there. So if I drew the slope of the graph here, it would be a relatively low slope. Over here, the slope is higher, so I can tell that the rate is increasing. This is not necessarily an exponential increase. It could be a quadratic increase. In fact, it often is in physics. The two are not the same thing, so be careful with language. If you say that it's an exponential increase, it's unlikely that it is. You'll learn about exponential functions in math class, probably when you're in your senior year. They're different from quadratics. Here we see another type of curve, rather. Here, as the independent variable increases, the dependent variable increases at a decreasing rate. So this could be for a cart that's slowing down, for example. The slope is decreasing over time. This one shows us that as the independent variable increases, the dependent variable decreases at a decreasing rate. Sometimes we'll call this an inverse relationship. These ones are unlikely in physics. If you get one of these shapes, you should show your teacher for sure, because you may need to check something in your experimental data. If we see a graph like this, this shows us that there's no relationship between the independent and the dependent variables. That doesn't mean that your experiment was a waste of time. It could be valuable information to know that there's no relationship there. In this example, this is exactly what we would expect for our experiment for mass and period of a pendulum. It turns out that mass has no effect on the period of a pendulum. All right, now you can work on some practice, and we'll design an experiment that we'll be carrying out soon.